Hi, my name is Jim, and today's topic is transformers, and what they're used for is current or voltage step up or step down, where step up means making the voltage higher and step down makes it lower. Also for impedance matching and for isolation. Now we're going to constrain ourselves to transformers used in the industrial environment. We're not going to be addressing radio frequency transformers or any other special types of transformers. So these are just basically iron core devices that are used at 60 Hertz. And to give you an idea what one looks like, what I've chosen is a doorbell transformer. And what we see is we have a core here. This is a piece of iron-like material, and what it does is it enhances a magnetic field relative to air for every turn of wire around it. This works on 60 Hertz, and this side of it's designed to be mounted inside of an electrical box in your ceiling. And this is a step-down transformer, and the output terminals here, as you can see, are screw terminals, and it's typically 18 volts. So it's not a dangerous voltage. Anything beneath 28 volts is considered low voltage, and you don't need to use Romex or wire like that to wire it up. So if you see one of these in your basement mounted on a box, or go over to your furnace, and you typically will have a little transformer mounted on its box also, and the output of that is 24 volts, and that's to operate your thermostats and so forth. And assuming that the air conditioner or heater is not on your furnace or your doorbell, if you put your finger on this, you'll feel it's a little bit warm. Now what this basically looks like, aside from the fact that it's a transformer, is that if it's not loaded, it looks like an inductor in series with a resistor. And that heat you're feeling is a resistive component of the wires dissipating I squared R. So from there, we'll proceed. So for word power applications here, and what we want is tight coupling. Now what that means here is that one winding and the other winding are very close together, so all of the flux, the lines of force produced by current flow, link both together. So we want very tight coupling, and there are good reasons why in RF transformers you don't want tight coupling, but in 60 Hertz, very important, because if it isn't, what we're doing is reducing the efficiency. So we can have two or more windings around some kind of iron-based core, and it has to be linked by a magnetic field, and we could have multiple windings on this also. We have the concept of a primary and a secondary winding, and that's not really the transformer, it's the circuit it's used in that determines what that is. Now, for example, I've taken two 24-volt furnace transformers here and wired them up because I wanted, say, to isolate myself from the mains power. So if I connect either one of these to earth ground, nothing bad happens. If I put a scope ground clip on either of these, nothing bad happens. If I put a scope ground clip here, I'll take out a circuit breaker, melt the clip wire, sparks, not pretty. So for this transformer, this is the primary, the 120 volt side, and the secondary is a 24 volt side, and then I'm feeding this into the transformer, we could say backward. But for this transformer, the 24 volt side is the primary, and the secondary is the 120 volt side. So the word primary and secondary are relative to the way the transformers are actually used in a circuit. So I could end up with an isolation transformer here, and I may have to do this. I burnt my isolation transformer up a couple months ago, and the stuff I work on is just too dangerous not to run isolated. The linkage of flux, so say we can have current flowing here, that's going to grow and cut the secondary windings and induce a voltage in it, and then if current flows in the secondary winding, it's going to build up a magnetic field also and cut the primary. So that's called mutual induction because it goes back and forth in two directions. So current in the primary affects voltage in the secondary, and likewise current in the secondary affects voltage in the primary. So they're interrelated. What happens on one side is going to somehow reflect into what happens on the other side. It is desired to have the flux linkage equal 100%, and basically, again, like I said before, all of the flux is cutting the secondary winding and none is per se wasted. And that's called a coefficient of coupling, and this is just background information, is the amount of flux which is mutually coupled divided by the amount of flux in the primary, and again the desired ratio is a 1.0. So we don't want any leakage flux, can be avoided if possible. Okay, getting into some key formulas for transmitters is we introduce lowercase a. It's unitless, it's a ratio, and what n is the number of turns on the primary divided by the number of turns on the secondary. Okay, so NP over NS is equal to the voltage of the primary divided by the voltage of the secondary. So the voltage is directly proportional to the turns ratio. Easy enough. But the current is inversely proportional. Now when we get into some examples, you'll see why that is. If we step up the voltage, we step down the current, and subsequently if we step down the voltage, we step up the current for a given load. So you have to be very careful with this guy here. I had an air purifier that I bought for $12, had a bad transformer, and I couldn't find a part number on it. I did not know the voltage of the secondary, so I sat in the kitchen and unwound the primary. Every 100 turns I put a mark on a piece of paper. There were 2,000 turns on the primary of the transformer. And then I did the same thing with the secondary and then replaced it with a 24 volt transformer. It was really 22, but I used 24. And it's right over there working now. So if A is less than 1 in the circuit topology, it's called step up, and if A is equal to 1, it's an isolation transformer. It's 100 volts in, 100 volts out, and if A is greater than 1, it's in the step down function. So A is just a short way of relating the ratio of the voltage to the secondary voltage, primary voltage to secondary voltage. So for example, if we have find Vs, A equals 3, Vp equals 10, this is our equation. Very simple manipulation, means that the secondary voltage is 3.33 volts. So no magic in lowercase a. Power, and what we're going to do here is assume 100% efficiency. Unfortunately not the case in the real world, but we're going to start there. So what we're going to say is in the secondary here, it's 40 volts, and we're going to be dissipating 40 watts in this resistor. And because it's 100% efficient, the power in the primary is also going to be 40 watts. So P primary is equal to V primary times I primary, and what we see is that we have I primary equals P primary divided by V, we're doing 10 volts, V 10 volts, and that ends up being that the primary current is 4 amperes. Now let's kind of put that into perspective for a minute. Since we have 40 volts, this is a step up. 1 ampere is going to be delivering 40 watts into this resistor. Now on the other side of the transformer, the power has to be the same. Therefore 10 volts and 4 amps is also going to be equal to 40 watts. V10, let me put a little V there so I don't make that mistake again. Okay, so look at this carefully and you should kind of get the flavor of what's going on in here with regard to the voltage current relationship in the secondary versus the voltage and current relationship in the primary. Now, what if it isn't 100%? Suppose it's 90% efficient. And realistically, remember we have I squared R losses in here. And we'll talk about losses a little bit later, but can't have 100%. So in the case of 90% here, and we're going to say again in the secondary we have 40 volts, 1 amp, and 40 ohms. What we do for the primary now is just take the power in the secondary and divide it by 0.9, giving us primary power of 44.4 watts. So the primary power is a little bit higher than the secondary power to make up for the inefficiency. Now, if you ever do this and end up with a number that's less than the secondary, you made a mistake. So that's the safety factor. So we could say then that the primary current, which we found up here, right there, would now be equal to the power in the primary divided by the 10 ohms, 4.4 watts, and we see that that goes from 4 amperes up to 4.44 amperes. So efficiency is going to be taken into account just as we have to do Kirchhoff's laws everywhere. We can't gain or lose power. We have to account for all of it. So this additional 4.4 watts could be some I squared R here, I squared R here. I haven't talked about this, but we could have some eddy current here. We could have coefficient of coupling, not 100%. A lot of things can contribute to that. So once again, I feel super motivated to make sure that we get the inverse relationship. Vp over Vs equals Is over Ip equals A. So current's backward. And now let's talk about losses. As I mentioned before, in the primary we have I squared R losses. We have wire, current flows through, that's that. We have I squared R in the secondary, so that certainly is going to be a loss, and it's going to manifest itself as heat. Then we have eddy current. It's kind of a strange guy, and I drew a weird transformer here. I've got the primary windings around this toroid, secondary windings coming off the other side, and if you look at this carefully, you'll see that the toroid itself looks like a one-turn secondary. So current is induced in it that flows back and forth, and this does not transfer any energy to the load. This is actually a current flow. Now, cores typically aren't made like this, and a lot of advancements have been made to make the core such that electricity cannot flow through it, but magnetic field can. One of the types is called an E-core, and I'd have to take one apart to actually show you what it looks like. But eddy currents have basically been severely reduced from modern transformers by reducing by eliminating basically an electrical path in the core itself. Then we have hysteresis losses. This is going to be a little strange. So just think about a nail, and you're going to wind some wire around it, and you're starting out where the nail is completely unmagnetized. Well, as you increase the magnetizing force, which is ampere turns times the length of the nail, the flux density, that's the flux per unit area, is going to increase linearly until that nail starts to saturate. So one of the things about a metal iron core is that you can reach a point where increasing the current further and the turns going around it will not result in an equal increase in the flux. It's kind of like it's full. Can't fit any more in it. So we start at 0 and we come up, we had saturation. Now I'm going to reduce the magnetizing force, and that just simply means that I'm going to reduce the amperage through this coil, and I'm going to track backward on red. And what I see is when I have 0 current flowing, I still have residual magnetism. So the result of this is I end up with a permanent magnet. It may not be very strong, but yet it's still there. And then I have to run the current in the other direction until I actually get the nail to a point where it's completely magnetic free. There's no flux in it at all. So that produces a loss. Now if I keep current going in the other direction, and all I did is reverse my power supply on this, I'm going to reach a point where it saturates, and then again reducing the current flow, I end up with a point where there's no current flowing, but now the nail has residual magnetism. The polarity is different. The north and south poles have changed, but it's again a permanent magnet, and I have to have the current flow in the other direction. This would be the original direction, until I can completely eliminate the magnetic field in the nail. And then continuing on. So once we start out, basically we're tracing the red and the green forever. Now what would be good to happen is that these two, the red and green lines here, collapse. The closer they are together, the lower the hysteresis. The saturation point in an industrial transformer, or for mostly any transformer, is to be avoided. And we'll discuss that in a minute. So restating this, H is the magnetizing force, and it's equal to the ampere turns, which kind of makes sense, times the length of the material, the size of the nail, and the flux density. That means how much flux sits in per square unit of the core. So this is called a BH curve. It's very common in any magnetic circuits book. So this represents a loss because you have to add energy to get back to zero. Okay, let's talk about saturation for a little minute. Air core can't saturate them, and this would be an example of an air core inductor, and if I wanted to, I could wind another turn inside of it, and basically I could force as much current as I wanted through this core, of course till the wire burn up, and the flux would reside inside of the core and come out and fold around. But there'd be no limit to it. I could not saturate air core. The more current I put in it, the more corresponding flux results, till the wire burns up. So if we were to look at this, what we would see is that we have the magnetizing force, and that's ampere turn length, and the flux, and we get our magnetic field. And note the slope of this. It's relatively shallow. And this is the problem with using air cores of 60 Hertz. Now if we put a piece of iron in there, the inductance of this thing goes from low to large. The problem is if we're using iron, we're going to reach a point where we can't increase the flux inside the nail by increasing the current flow through the wire around it. So we end up at this saturation point, and that's not a good thing, and the reason it isn't good is because take a look at a transformer that's not overloaded, and what we see is that the current's sinusoidal. Now if we saturate this, and what I just said here is low load resistance, when that hits saturation, basically the flux doesn't increase, it doesn't change. Therefore, there's no changing flux to further inhibit current flow, and the current flow gets these little bumps on the top of it. And that increases the heat in the transformer. And we're going to make a little bit more sense out of why this happens in a minute. But for the time being, that's a very bad current to have. If you see that, of course you have to put a resistor in and look at it. It indicates that the transformer is overloaded. So we have several different types of transformers, and one that we see frequently is the auto transformer. And this is typically wound on one coil, but to get the point across, I've kind of showed two windings added together. So if I have a 100 volt primary and a 10 volt secondary, and I add them series aiding, I get 110 volts, and we'll say we have 1 ampere flowing. So the rating of the transformer then is 10 volts and 1 ampere, and it is 10 volt amperes. Now remember, a VA is the correct unit of rating for a transformer. It's only 10 VA, even though there's 110 volts secondary. Now let's do the same thing with a regular transformer with 110 volt secondary. Again, 1 amp flows. Again, we have a load of 110 volts turning across this guy, but the transformer rating now is 110 VA. So this transformer is very, very large compared to this guy, because the transformer part of this is only producing the 10 volts. Nothing's free. This does not isolate. This does. So The auto transformer abusing the secondary to increase or decrease the primary voltage is a nice thing to have, but it also has advantages and disadvantages. So using this in step down, I have 10 volts and I've connected it, so these are series opposed, and that gives me 90 volts. One time, this is my way of saving money, electrical bill in this house, because the power is proportional to V squared, would be to lower the house voltage via this technique to maybe 105 volts. At the time I was thinking of doing this. The problem is it still takes the same amount of energy to heat the water tank. Things like that, which are absolute energy dependent, so I never got around to doing it, which is probably fortunate. So here we have a transformer which is stepped up, and you see it as one contiguous winding, and that's typically the way an auto transformer is wound. The things that you've seen previous is just an explanation of how it works. And this would be a step-down auto transformer where the tap is underneath the 100 volts. So we can have a transformer with multiple voltages, step up and step down, and all we would do would be have taps on the primary and a couple extra turns here in case we wanted to go above 100 volts. So if the line voltage were low and we needed a higher voltage, we could select the very top tap. I just still worked on a guitar amp this summer, and its transformer had this about 25 watts or so for somebody. Let's take a look at the use of transformers in power distribution, and I think this will kind of make a lot of sense. Suppose we have an electric company, without getting into a lot of numbers. They're outputting 100 volts, and we're the user in our house, and we have some resistance, and whatever our load is here, we're drawing 1 ampere of current. So the 1 ampere is flowing out and flowing back, and we're going to say that the transmission line is long enough, or the wire is thin enough, or both, that we have 1 ohm of resistance in each wire. So the losses from the standpoint of the electric company are 2 watts. They're going to lose 2 watts here, and my electric meter is not going to record the loss in the transmission line. So that's not exactly a desirable situation, and this is what would have happened if Edison won the war, AC versus DC, when he was arguing with Westinghouse and Tesla. And as you probably know, AC won. Now suppose we put a transformer in here. This is really cool. We're going to take our 100 volts and our 1 amp here, and we're going to step it up to 1,000 volts. And since the power is going to be the same, and we're assuming now that the efficiency is 100%, the current drops to 100 milliamperes. And if we multiply 1 amp times 100 volts, we get 100 watts. If we multiply 100 mils times 1,000 volts, we get 100 watts. And then we step it back down for our end user, so he gets about 100 volts. So the losses now, I squared R, are 100 milliamperes squared times 2 ohms, drops from 2 watts to 20 milliwatts. This is why electric companies step voltage up into the hundreds of thousands, is to get the current down as much as possible to minimize the I squared R of their transmission facility. I used to run under a high tension line, and it was raining in the morning, and on a damp day I could hear it hiss right underneath it. Didn't particularly like that too much. How secondary load is transformed to the primary, and this is a non-math model, so I kind of want to explain this in a way that you can picture what's happening, because this is the way I understand things better if I can get a mental image of it. And what we have is a transformer, and the secondary is not connected, so it looks like this, an inductor. And the key equation for inductor is VL equals L di dt. Now for this model, and this is leading into inductive reactance, which I should kind of make note of that. You probably haven't been exposed to before. I mean, this is solved with sine waves and so forth, but not with the picture in your mind sort of thing. So we're going to make the IDT the independent variable, and we do that by feeding our inductor with a current source, and we're going to rate this at 1 amperes. Now, what we know about current sources is that a 1 amp peak of a sine wave, and I do need to tell you that everything is RMS up to this point, this is 1 amp peak, is going to flow no matter what terminal voltages are. So that's the way a current source works. And when current flows, let's not look at this yet, it builds up a magnetic field, and that magnetic field cuts the windings. Now when it cuts the windings, it induces a voltage in the windings. And guess what? That voltage opposes the current that produced the magnetic field. So effectively, what this looks like is that we have a voltage source in series with the inductor, which is dependent upon the actual flux, the current flow in the magnetic field. This is a phantom part. It's not really there, but it is there from the standpoint of that it's caused by the current flow cutting the wires. So this is inducing a counter EMF that opposes the sourcing current, and what we know is that dI/dt has to do with how fast a waveform changes. It's kind of like delta I over delta t. Let me fix this for a second. There we go. Except it's instantaneous. So if we take a look at a current waveform here in blue, is what we see is the rate of change. What we're looking at is the slope, the rise over the run. Change as fast as here in a negative going direction, and the top here, m is going to be equal to 0 instantaneously, and it changes the fastest going in the positive direction here, and m is 0 here. So we have fast change going positive, 0 change, fast change going negative, 0 change, and so forth. So if the flux isn't changing, what happens is that the voltage induced is going to be 0. So at this point the flux isn't changing, and the voltage induced across this is going to be 0 volts. At this point the flux is changing the fastest, so our counter EMF is going to be a maximum. Here the current's changing is not changing, therefore since the flux isn't cutting the coil anymore, the voltage induced is going to be 0. And again, here is change fastest in the positive direction, so the voltage induced is going to be maximum. And if we trace and connect these 5 points together, is what we end up seeing is that the current is going to lag the voltage by 90 degrees. So we can kind of picture that in our mind's eye by saying that the counter EMF is responsible for the phase shift between the voltage and current in an inductor. And that's kind of a picture that I can live with in an attempt to understand what's really going on inside of an inductor. Some of the stuff to me is not obvious. Now, let's take that thought and add in a secondary with a load. So this is where we started. We had our counter EMF here. Now we have the secondary, which was unloaded before, so it didn't count. Yeah, we cut the wire and we induced voltage in it, but there was no current flowing. Now, if we have a load, secondary is going to produce flux also. So the primary flux is cutting the secondary, and the secondary flux is cutting the primary. So what effectively happens is the flux from the secondary reduces the counter EMF. So when we load the secondary, more current flows in the primary. So that's the way the load in the secondary is represented in the primary side of the circuit. Now, if we got into this very deeply, is we would have phasors all over the place showing this, what would happen with a reactive load and this and that. But this is a pretty good understanding of how it really works. Why a load on the secondary causes an increase in current in the primary. Okay, again, transformers are rated in VA, not watts, and a little example here. Suppose we had 10 volt transformer secondary and a 10 ohm load, and we know that we'd have 1 ampere flowing here, and if we put a capacitor in parallel with it, we would have some current flowing through the cap, and I would not have to calculate this here, knowing this current, square root of the sum of the squares, but this current has to be greater than 1 ampere. Has to be. So this transformer would be overloaded if I put a capacitor here, even though that capacitor is not going to dissipate any energy. And it isn't. It stores and returns in an electrostatic field, just like an inductor would store and return in a magnetic field. So let's talk a minute about variable transformers. And what this arrow means is kind of like a shaft on a resistor, and we'll be able to see one of these in a DC circuits lab. And these additional windings mean that we can go above 120, say, to 135. And variable transformers are fairly expensive, but sometimes they're nice to have. And the one I'm going to show you is very small, so you're going to have to look hard to see it. There it is. It is variable. And there's the knob. And what this is doing, I'll set this down, is it's touching the wires as wrapped around the core. So, I don't even know if I should try to draw this here. The core looks like a donut, and the wire is wrapped around it, and this side of the wire is bare. So when this slider comes by and it's on a piece of carbon, it touches the ends of each piece of wire and picks off, if you will, a voltage that corresponds to where the dial is set. Now what I use this for, and they're very useful, like in the motors lab we're going to be setting up voltages specifically so we're not dependent upon whatever comes out of the wall. But what I use them for is if I'm working on an older piece of equipment or equipment that has not been turned on for a long time, is I plug it into this thing, watch the power supply voltage, and bring it up very slowly. So if I don't see things working out okay in the circuit as I increase the voltage, I can turn this off and start to troubleshoot before I blow a part out of the board or whatever else. So that's a variable transformer. They come in very handy when you need them. So that'll do it for transformers, and thank you for watching.